Today I'll be presenting on precast hammerhead vent caps. Opportunities, considerations, and challenges is the title that I've given. On to the agenda for today. We'll start with a short history of the precast in Texas, just to give a perspective on where we are. Followed by a discussion about an opportunity, a project that we did where we got to use some of the pre-stressed precast caps, some of the design features of the precast cap, some considerations, some challenges on the project, and we'll conclude the presentation. So talking about history of precast in Texas, we started doing some precast in 1990s, early adoption, followed by some standardization in early 2000s. We got a push from accelerated bridge construction in about 2010-12 timeframe, and that's followed by pre-stressed bent cap innovation with a standard being released in 2017. So a little bit closer on the era. So TxDOT began using custom precast reinforced concrete bent caps to reduce construction time on congested urban project. So that's why it started. The first, or almost one of the prominent project, was I-45 in Pierce elevated in close to Houston downtown. This project was done in 1996. So in this project, the existing columns were reused and with a precast bent cap, and this is sort of the connection used at the time. So the primary benefit of this project at the time was like the construction delay was estimated at around $100,000 per day in the urban environment. Moving on, so building on the success of these early projects, TxDOT moved towards standardization in early 2000s. Firstly, it was just for the connections, then it follows with the more detailed precast, reinforced, and pre-stressed designs. This period marks a transition from experimental use to a broader adoption statewide. In this picture, we have State Highway 66 over Lake Ray Hubbard in DFW area. This project was done in about 2000, and this is the picture of the connection that was used at the time. So following this, we got a big push from accelerated bridge construction in around 2010, 2012. So this coincides with TxDOT releasing a statewide standard for precast reinforced concrete bent cap. This is a snippet from that standard. It is PBCRC standard. Following this, TxDOT research demonstrated with the academic institutions demonstrate the advantages of pre-stressed precast bent cap, primarily in the crack control and durability, also construction schedule. So with this, in 2014, first large-scale use occurred in Bear County. The project is for Loop 1604. Quickly following this, in 2017, TxDOT issued a precast pretensioned bent cap (PPBC) standard, which is a snippet here. It's the standard for the whole bent cap, not just the connection. So following this, a reminder, Texas has the largest number of bridge inventory in the US, making construction speed and repeatability critical. Precast bent caps aligned well with TxDOT's long-standing use of standardization of superstructure elements, girder decks, and panels. Pre-stressing also allowed TxDOT to design caps with zero tension under dead load. This significantly reduced long-term cracking. So now precast bent caps, reinforced or pre-stressed, are mainstream TxDOT substructure option. Now moving on to the next section of the presentation, where I'll introduce a project, and the project provided us an opportunity to go with the pre-stressed precast hammerhead bent cap. The project is I-35 NEX Central, located in Northeast San Antonio. It's just by the cities of Live Oak, Selma, Surge in Bear, and Guadalupe counties. The project is about 9.5 miles with a design build cost of around $1.5 billion. The contractor for the job is Alamo NEX Construction, which is a joint venture between Ferrovial and Weber. The construction started in 2022 and is expected to be finished in late 2027. So in this project, there are over 800 spans, more than 4,700 concrete beams, more than 1,300 columns, and more than 6 million square feet of breeze decks. In this project, ultimately 346 bends were redesigned as pre-stressed precast hammerhead bend caps. In this presentation, I'll be taking an example of one of the bends that is representative of all the challenges and consideration that we did for these 346 bend caps. In this picture, it's the bend that I'll be using to feature this is highlighted in the blue box. So this is the bend during construction. So this cap is 40 foot long with two 4-inch end star pieces, which I'll get to a little bit later in the presentation. It supports TS70 girders, 127 feet and 133 feet spans in either direction, about 42 feet roadway, and supported on a really tall column of 55.5 foot. This particular pre-stressed bend cap is 6 feet 6 inches deep, with 3 feet 6 inches at the end. The cap width is 4 foot 11 inches. So now let's move on to the next section of the presentation, which is design features of this pre-stressed precast hammerhead bend cap. So we'll be looking at this bend cap in detail, and these are some of the components of the pre-stressed bend cap. So we have, towards the middle, we have a CMP, corrugated metal pipe sections, 4 of those that allow us to connect the precast bend cap with the columns. It also features a drainage pipe built into the precast cap. There are lifting loops supporting the hauling and erection of the precast bend cap. There is a block out and some details at the end for the end star attachment. And there are some pre-stressing strands and reinforcement. There are some column dowels, grout for the gap between the precast cap and the column, some drainage pipe connection detail, and some cast-in-place support for the temporary condition while it's being erected, and some compressible bedding material. Now this kind of looks busy and crowded, and that's kind of the point of this image. So it's here to showcase like how closely everything fits and why detailing is super important on this kind of design. And I have some pictures of the columns ready to receive pre-stressed precast hammerhead bend cap and an installed condition with some formwork still in place for the grout portion. Now let's move on to the next section, which is considerations. I'll start with lifting, hauling, and erection. So things we need to consider for lifting, hauling, and erection is lifting weight. In this project, we have precast bend cap from 6 foot 6 inches to 9 foot deep. The length ranges from 40 feet to 52 feet 6 inches, and they weigh from 180,000 pounds to the heaviest one being 300,000 pounds. So lifting weight is a key consideration. Location of lifting loops is also super critical. So these are the lifting loops shown here in the image. So if we can space out the lifting loops, it helps with the stability and it makes construction easier. Now, if they are closer, then it means we have to use a spreader beam. It was not preferred option because of the cost of the spreader beam. But we only managed to get these lifting loops as far out as shown here due to some other stress considerations we'll get to a little bit later. And another consideration for lifting, hauling, and erection is CMP, corrugated metal pipe diameter and placement. Next considerations is stress reversal. During the erection, the bottom section will be in tensile stress temporarily, as shown here in the image A by green dots. And in the final condition, which is shown by the image in B here, permanent tensile stress will be at the top during service. And these reinforcements shown on the sketch are there to handle respective tensile stress as well as permanent steel stress. Moving on, so I kind of show here two cross sections of the deep portion of the cab. The one on the left is with the CMP section, and the one on the right is without the CMP section. High tensile stress occur at the bottom, primarily in the CMP region for a short length. And this is during the lifting and hauling operation, primarily during lifting. This region, while under tensile stress during construction, will be in the permanent compression field later on. So the tensile stress during this stage is caused by pre-stressing, because the pre-stressing strands are located towards the top, as well as bending during lifting and hauling because of the support points located at the lifting loops. And to mitigate some of the stresses here, we have located some strands towards the middle of the cab, as shown here, so that the more of the cab is in the compressive field. So the next consideration is cab to column connections. So a tension compression couple was ultimately used as the design for the CMP bars. Development of dowels is a consideration that needs to happen within the CMP space available. We also need to consider about the fit of the rebars inside the CMP, and cap slope and cast in place support also plays a role in the connection. And we need to come up with a grout system that works. And we need to think about the drainage pipe connection here. Now, talking a little bit more about the tension compression couple. So we ultimately used precast only for concentric caps or a very slight centric caps, about 1 feet or so. So in this, the compression centroid is assumed at the CMP location. In reality, when the grout is engaging, the concrete just below the cap engages, and this compression centroid is slightly better than shown here, meaning it's a little bit to the right, with a more arm length between tension and compression couple. But ultimately, we decided on this slightly conservative design method, so that we don't have to rely on the grout. And in addition, the tensile stresses in the CMP bar was limited to 0.6 FY, as is standard practice from AASHTO for crack control. Now we did some optimization for pre-stressing strands. In the sketch here, the big red dots are the longitudinal reinforcement. The green dots are the slots available for pre-stressing strands, and the red dots are the pre-stressing strands actually used for this example bend. In this example bends, we use 49 strands, but we optimize this for all of the design, and the location of the strand is different for different designs as well for this optimization. Moving on, we did some optimization for longitudinal reinforcement as well. So we used bundle bars only where needed at the bottom as well as at the top, which is the image on the left here. Similarly, for transverse reinforcement, we have varied the number of legs as well as spacing of the stirrups, so that we reduce the quantities overall. So towards the end, we have tightly spaced stirrups here. This is for splitting resistance of the pre-stressing strands, followed by wider spacing. And then again, the spacing tightens because we are closer to the CMP section, and we are needed to provide a confinement as well as some high shear demands at the end. But mostly this is atypical towards the middle because of the confinement requirements for the CMP. Now, some drainage considerations. So for the bent caps where we needed to have drainage pipe embedded into the cap, we embedded them in the precast design as well. It's connected to the columns with a 10-inch to 8-inch reducer, and it connects to the column pipe. Now, in the end, we did a mock-up trials to make sure this is a valid method and it works, and it was a success. For the drainage pipe, we also need to consider about the location of the transverse, longitudinal reinforcement as well as strands. Therefore, the image on the right is kind of showing how this how the placement of the drainage pipe affects the stirrups and longitudinal bars and such. So now the final items of considerations I want to talk about is the aesthetics requirement. We do have a Texas star. We needed to place it at the end of our caps. Now it's very easy to do with a reinforced concrete bend cap, but it presented a little bit of challenge for the precast option. So in the end, we came up with a connection detail using blockouts at the end, and the end star piece itself is a precast reinforced concrete. And when everything is ready and the cap is ready to receive it, we just place it there and then make the connections in the grouted area. So this is something we have to come up with for this project. Now moving on to the next section of the presentation, which is challenges. The first of which I want to discuss is the transform section. Now in areas with now for the transform section, the practice, the image on the left shows the concrete section properties used to evaluate the tensile stresses, which is the accepted and common practice for TxDOT. Now the image on the right is where we use concrete plus steel transform section properties. This is what we used to do school homework problem. That's this method here on the right. Now the method on the right will provide, I guess, a more realistic but also lower stress demand. But this not being a common TxDOT practice, we asked the question still, and TxDOT still decided to go with the gross concrete properties option. And talking about tensile stress, just a background. In the temporary condition, the limits are slightly higher, but we have to use the initial concrete strength. And for the final condition, it's a service condition. The limits are a little bit lower, 0.19 square root of prime C, limited to 0.6 KSI. Now, Texas did relax some criteria for us in this project. So at the CMP location, they allowed us to increase the temporary stress to about 0.6 KSI using this method, provided we use gross section properties. And when we consider just 30% of the dead weight, and they also mandated a maximum crack width of 0.008 inches calculated using ACI method. Now we rarely have to use this criteria because most of our caps were able to satisfy this requirements, but there may be a few instances where we use this relaxed criteria. And again, this is only for the CMP section, and the idea here is like the sectional design method is kind of conservative because it does not consider the stress transfers around the CMPs. Now, this challenge is kind of gateway for us to talk about next challenge, which is the small cross sections. We had to reduce the CMP diameter at the top because we needed more space to fit more strands, kind of shown in the image here. And we also needed more concrete area to satisfy the stress requirements. So because of this, it created some more challenge, which is how to cover the gap between the two CMP diameters. And we worked with a fabricator to come up with a system. And this also reduces length available in the cap to develop the dowel bars, which is our next challenge. So we have to use bundled bars. We needed to use bundled bars, so which kind of is detrimental to the development length requirement, which we managed by considering spacing and clearance of those bundle bars, as well as taking help from the transverse spirals and hoops. We also use higher concrete for the CMP section to mitigate with the development length. In this example, total development length available was 4 foot 10 inches because of the 2 CMP diameter with 2-inch clear. And this is more critical for smaller caps. It was not an issue for the larger caps. So this requirement for spirals and hoops we dispensed with for our larger caps. So the contractor were only supposed to use as necessary for the constructability purpose. But for the smaller caps, we mandated the use of are design spaced hoops. Now another challenge was cap cross slope and grout. So this detail kind of shows what we ultimately decided to do. So we included the cross slope in the top portion of the columns with some rebars, maintaining 2-inch constant gap throughout the length. And at the ends, we used 2-inch compressible foam material so that we maintain the design section, as well as use the CIP supports. And to make sure this works, we did some mock-ups, which is shown in this image here. So we cast 2 pieces based on the design and then grouted them as per the detail. And we also included the CMP as well as the drainage connection in the mock-up. And then we cut open this section to see if the grout is performing as intended or whether there are any gaps in the grout or not. And it was a success. And we moved on with the final design. Another consideration, another challenges that we have on the project is for the fabricator and contractor needed to cast 4 or more bends at once in series for efficiency. Now, the sequence of bends cast together was determined by construction sequence. So our previous optimization was based on the demands on the similarly spanned sections and similarly sized cabs. Now that's kind of out of the window because we again reevaluated the strands requirement based on the cabs that were being cast together. And this was done with good success. Ultimately, we added strands. We did not reduce for most of the bent caps, and for some of the caps, we used debonding so that some of the strands remain inactive. So this was a challenge we faced later on the project. And this standardization was done within the limits of applicability to improve construction efficiency. So moving on to the conclusions section. In the first section, I'm talking about cast in place versus precast caps and pros for each of those. So cast in place cap is regular routine design and construction. So everybody knows what to expect with these. Unique design, fabrication, and erection considerations are not introduced. Transportation and erection of heavy concrete component is avoided. The pros for the pre-stressed precast is improved construction efficiency, reduces on-site labor and improves safety, accelerated construction schedule, improves quality control and durability of the concrete, and minimal on-site impact due to quick installation. On the next section of conclusion, I want to focus on the pre-stressed precast hammerhead bend cap. So precast construction has come a long way, and that was the kind of point of the history discussion in the beginning. And a pre-stressed precast cap is very common now. It's probably present in every major construction. Pre-stressed precast cap comes with some unique challenges, more specifically connection design and detailing, how to ensure stress transfer happens, as well as how to make sure things fit together. Pre-stressed precast hammerhead bend cap improves construction efficiency, making a value proposition for large and complex projects, such as the example project. And there is a case for standardization, especially for the single column hammerhead bend caps. Since we are doing a lot of these and there are lessons learned from this project as well as many, many other projects for TechStart, we could do well with coming up with some criteria that will make some decision making easier. And this zero tension under dead load significantly improves the durability, as has been demonstrated in many projects as well as many research. That's all I had prepared. Now I'm opening the floor for some questions.
What about the precast cap? So column is cast in place.
Column is cast in place. So I did not include that in the presentation. So we made sure the CMP length and then the detailing stirrups around it is adequate for non-contact splice length requirements. So basically it's long enough and the horizontal transverse reinforcement is adequate for to support the non-contact splice. So it's basically bending at the point.
Very large project. You mentioned this was a very large project, complex geometry. So you showed one example with one set of geometry. So I gotta, did you have different sizes of the caps, and how did you minimize the effort the contractor had to deal with to maximize efficiency of the design?
Right. So I showed one smaller of the caps because the detailing considerations for the smaller cap was more challenging than the larger caps because of the space available. Yeah, so we try to group as many of the designs together as possible for different cap sizes. And there were different cap sizes, but we did not use a single cap size to help with the formwork requirement and the templates for the pre-stressing strands. And also there was always a batch of caps that was designed together and then sent to the contractor together. So that was the original idea. However, some of that needed to be revised based on the construction scheduling, not necessarily because of the designs. So that we accommodate later on. And from the beginning, we worked with the contractor and the fabricator to make sure all of us are in the same pace. And we also came up with a design system so that we can apply to multiple caps. So that's how we handle about 346 precast cap design. Right. So the original idea was like there would be some material saving as well, which really did not happen because of this stress requirement, and we needed to use a lot more rebar for the precast option, especially for the smaller caps. Now, most of the savings, if not all of the savings, came from the schedule impact. So we could do a lot of batch construction on the side, and there was a limited impact to the traffic control operation, as well as the installation was pretty quick. So it was a schedule related construction savings more than the material related construction savings. And that's quite substantial as well. I don't know the exact figure, but they in the end decided to change a lot of originally reinforced concrete caps to precast cap. For the precast caps. So essentially, these precast caps were cast in the same yard where we do the pre-stressed beams. So it was a much more controlled environment, and our clearance and clear cover requirements were even more strict than for the pre-stressed reinforced pre-stressed design. On top of that, we did not allow any of the stirrups to directly be on top of the strands as well. So there was always a 2-inch gap. And then we did some inspections on the site, I believe. So together with these things, we believe we have much better quality control than on the casting based construction. Thank you.